welcome to today's project spotlight on Passive House in hot climates. My name is Jessica Grove-Smith, and I'm a senior researcher and joint managing director of the Passive House Institute, the research institute based in Germany and responsible for the International Passive House Standard for highly energy efficient buildings. More and more buildings are being built to the Passive House standard around the world, ranging from single-family houses to multi-family buildings to much larger and much more complex building typologies. It's a great journey to be part of, and we're really encouraged by this growth and by this uptake worldwide. Still, realistically, I have to say that there is a lot that we all can, and I think we all must do to really transform the market and the sector for better buildings, healthier buildings and climate-friendly buildings. Events like this one, I really like them because I think they're really important to share experiences across borders. Experiences from real-life projects, including the lessons learned, things that went well and things that were particularly challenging for the project team. So I'd like to thank Passive House Philippines for organizing this event, the speakers for presenting the project, and again, a very warm welcome to all of you who are here today for the learning about Passive House in hot climates. We at the Passive House Institute, together with our membership network, the International Passive House Association, we advance research, we advance professional training, capacity building, and we do a lot of quality assurance work for highly energy efficient buildings and high performance building components, whether it's insulation solutions, whether it's windows or ventilation systems, for example. The available research and the many realized implemented projects that are out there, they show the benefits of building and of living or working in an energy efficient, healthy and comfortable building built to the Passive House standard for new build projects, or the ENERFIT standard, as we call it, for retrofit standards. Now, as the Passive House standard was initially defined in Germany, where the Institute is based, some who are still new to Passive House might have questions about how it applies in hot climates, like in the Philippines. I can assure you, as a physicist myself, that the same laws of physics apply around the world, and I assure you that Passive House delivers in hot climates as well, where it's obviously all about reducing the cooling. Today's project spotlight is about a very special project, which shows exactly how this can be done. And the two speakers, Jordan Parnas and Dylan Martello, they're two very experienced Passive House practitioners, and they'll be sharing how a garment factory in a very hot and humid climate of Sri Lanka was transformed into the first certified ENERFIT building in that part of the world. Now, as you'll hear from them, one crucial aspect of energy efficient design in hot climates is to keep out the heat. Sounds logical, sounds intuitive, but you have to think it through and really apply it consistently. So for example, with good insulation, with carefully managing sizing of windows and appropriate shading, as well as keeping the heat loads within the building low in the first place, for example, with efficient equipment. Another important and really interesting topic is how to manage humidity in a humid climate. A really effective approach here is to use mechanical ventilation with humidity recovery, because that will ensure that the people inside have fresh air, but without bringing in all of the humidity from the outside air. The Passive House Planning Package, or PHPP as we call it, was developed by the Passive House Institute specifically to help designers find the right components for their Passive House. It's a design tool which helps you choose the right components for your specific building and in your specific climate. Now, as you'll see in today's example, using the PHPP and the Passive House methodology as a whole leads to really significantly reduced cooling needs for buildings in hot climates. And it's not only the energy needs for cooling as a whole. One big benefit is that the cooling peaks are also really substantially reduced. And that means you can use smaller systems, you can use more efficient systems, and there is much less stress on the electricity grid. So in addition to the benefits of your actual just local building in itself, there's also benefits for the energy supply, which is a benefit for the society as a whole. Not to speak about the reductions of carbon emissions, of course. Now, I'm really into this topic. I'm convinced by the benefits and by the opportunities of energy efficient buildings, so I could spend a lot of time talking to you more about Passive House and Passive House in hot climates, but I don't want to keep you from today's webinar and diving into the details of this specific project. So if you want to learn more, feel free to reach out to us at the Passive House Institute, reach out to Passive House Philippines, and I strongly recommend that you take a look online. There's a lot of information already available to go and read and learn. In particular, I can recommend the online Passive House resource, which we call Passipedia, and you can find on passipedia.org, where there's a lot of information and resources dedicated to Passive House in different climates. There's always a lot of learning from actual implemented projects, so find a project in your area or in other parts of the world and speak to people who are already doing this from their learnings. Before I close, one last important thing, because we're here today not only for the project Spotlight, but also to celebrate the launching of Passive House Philippines. So big congratulations go out to Norman Garcia and his team. We're really delighted by the founding of an organization in the Philippines that is dedicated entirely to Passive House. We wish you all the best on your journey, and we really look forward to the prospects of working together to fight climate change and to provide healthy and comfortable buildings for all. So a big thank you and a big congratulations. And now, everyone, please get ready to take some notes and enjoy all the learnings and the insights from this project Spotlight, showcasing how Passive House works in very hot climate conditions.
Energy efficiency and comfort are relevant to each other. So we cannot talk about energy efficiency without uh, talking about comfort. Okay, so um, comfort, as you can see from the blue range, it consists of an infinite combination of indoor temperature and indoor relative humidity. So so this is the situation in the Philippines right now. So without air conditioning, um, the room temperature is at 25 Celsius, but the humidity is so high. However, if we use a standard air conditioning, as you know, um, standard active air conditioning can decrease the humidity. However, the room temperature will go at a very uncomfortable level at 21 Celsius. So it becomes chilly and uncomfortable because the humidity is still high. There is not enough dehumidification that is done by doing active air conditioning alone. Okay, so if we dehumidify but keep the room temperature higher at 25 Celsius, then it will be comfortable. So we're here to talk about passive house. So, but what is active? So active means you you need constant supply of electricity to provide energy. So similar to this water cooler, electric water cooler, in order to keep the water cold, um, it has to be continuously plugged in. And as you can see from the water bottle, it's not insulated, it's not airtight. But on the other hand, a sports bottle, a tumbler, if you pour a cold water 8 o'clock in the morning and you open this tumbler at 2 in the afternoon, the water is still cold. Well, the secret is just physics. It's airtight, it's insulated, and it's continuous. So let's apply this passive approach to building. So this is the 5 principles of passive house. So first, let's start from the bottom left. Uh, Continuous insulation. So a passive house has a continuous insulation all around. Second, passive house windows. For hot and humid climates, a two-pane window is sufficient. And then on the lower left, lower right, thermal bridge-free design. So, meaning the insulation that covers the building envelope should be continuous. So, I'll show you some diagrams later. And fourth, the building envelope needs to be airtight. And then last, you'll wonder, so how will people from inside the building will be able to breathe? So the secret is installing a adequate ventilation strategy called energy recovery ventilator that allows fresh air from the outside to come in, but capturing the high humidity and not allowing it to get inside the building. And passive house, this is a performance. So there are very strict criteria for hot and humid climates. So it sets a maximum limit of 15 kilowatt hour per square meter per year, plus variable allowance for cooling and dehumidification. And for the cooling load, it's very strict. It has the cooling load needs to be no more than 10 watts per square meter. And air tightness for new construction is zero point 0.6 air changes per hour. For retrofits, slightly relaxed at 1. And frequency of overheating, meaning uh, the interior of the building should not exceed 25 Celsius by no more than 10% without active cooling. And if there's active cooling, then the active cooling equipment should be adequately sized. And lastly, the frequency of excessive humidity, meaning the amount of water in the air should not that are greater than 12 grams of water per kilogram of air should not or absolute humidity at 25 Celsius should not be exceeded 20% at a time without active cooling or 10% with active cooling. And this is the thermal bridges I was talking about. So thermal bridges are any point uh, that breaks the continuity of the insulation in the building envelope. So typical examples are balcony, slabs, or any point penetration. Because on these points, for civil engineers, the it has to be rigid. It should be able to support the structure. Okay, and so this is the core or the heart of the passive house. So in architectural design, architects you all use BIM. So pretty much passive house planning package work the same thing. So this is the energy modeling software that is used in calculating the energy balance in passive house. And the good thing with the passive house planning package, this is in Excel. So everybody knows how to use Excel. And this is a very large Excel developed by very smart Germans. And yeah, okay. And then the output, it will tell you uh, the energy and comfort performance of the building. And passive house can be applied to both new construction and retrofit. Okay, so passive house originated in Germany so the first passive house was constructed in 1991. So take note, the word house is the German translation for building. So that's why you must be wondering why is the spelling of the passive house association HAUS. So it means so passive house literally means passive building, not bahay or house as we call it in Tagalog in the Philippines. And also take note, the passive house is an open concept. It's not a trademark word. In fact, there were attempts by many organizations, entities to trademark the word passive house, but the Passive Institute always try to argue that it should not be a trademark phrase. So if you can design and build a passive house there in the Philippines, as long as you use passive house planning package, then it's a passive house. So you really don't need to certify it. On the other hand, you're not permitted to use the term certified passive house unless it's uh, it's really certified by the Passive House Institute in Germany or the accredited certifiers worldwide. Okay, so some milestone of passive house. It was the passive house standard as we know it today was developed in 1998, and the Passive House Institute was founded in 1996 by Bo Adamson from Sweden and Wolfgang Feist from Germany. Can anybody please guess what are the professions of Mr. Adamson and Mr. Feist? Anybody guess? Are they architects or are they engineers? Well, the answer is neither. They're actually physicists. Okay, so that's why the Passive House Institute is really based on is a very heavily based on science, based on building physics, and even uh, our uh, uh, speaker for the welcome remarks, Jessica, is a physicist. So right now, the Passive House, as you know, as you can see from this map, originated in Germany. So you would definitely expect there are many passive house that are certified in Europe and in North America, and it also started to take some flight in Australia, New Zealand, but as you can see from the map, there's still none yet in the Philippines. And in almost major countries, there are passive house organizations and affiliates that are organized. And the Passive House Philippines was joined the International Passive House Institute as a member organization last year. And we're hoping to become an affiliate soon because one of the requirements to be affiliate is there has to be a certified passive house in that country, which we don't have yet. No, so we're just a regular member. So passive house, it applies to different occupancy, not just house or bahay. So there are passive house, social housing, school buildings, kindergartens, gyms, office buildings and factories. And right now, there are four known certified passive houses in hot climates that have similar climates in the Philippines. So we have in Indonesia, Thailand, Dubai, and Sri Lanka. And uh, uh, we're fortunate that our first two events, we're going to feature the certified passive house in Sri Lanka today and the event next month. Uh, we are inviting the architect of the first passive house in Thailand, and he's actually here with us today. Jay, he's an architect from Taiwan. So passive house is actually climate resilient. So this photo made news in the passive house community last year. As you're all aware of the wildfire in LA. This is one community in LA in which um, a, a lone passive house survived the LA wildfire. And you'll notice that in this passive house, there's no gutter, there's no gutter where ember can fall into. The house is airtight. So those passive house characteristic made this residential house survive the LA wildfire. And there are many buildings that are certified by other green building standards, even LEED Platinum, in which the passive house surpass in terms of performance, in terms of the energy use intensity. So the big question is, how do we scale this up? So it's impractical to put solar panels to every roof in the Philippines. So even if we put solar panels in every roof in the Philippines, it's not enough to meet our 2050 targets. And even if we do it, it's not practical, it's not scalable. It takes a lot of infrastructure. There are issue on storage. So we need a better approach, and that's where the passive house approach is. The passive house approach, let's reduce the energy load of the building envelope first through passive design. And then second, let's improve that's the only, after improving the building envelope, that's the only time we improve the efficiency of the mechanical system. And last, that's the only time we connect to the low carbon energy. So this is the hierarchy. And passive house works with, so I just want to clarify, passive house is not a green building standard. Passive house is an energy efficiency standard. because as you know, we have many practitioners from the green building community here. The green building is a large, it's a holistic approach, and it tackles many categories such as seating, urban planning, material circularity, and those are the things that passive house don't tackle. Um, so and locally, for example, locally, it also works well with Verde. Um, the Verde, they have, as you know, we have Verde professionals here. You have there are different categories in which a building earn a Verde certification by getting points from different categories. But passive house works well because a Verde certified building that incorporates passive house principle would get maximum may get maximum points for energy and thermal comfort. And also it also, I think it also works well with green by the Philippine Green Building Initiative. So the Green Building Initiative, EDGE, um, these are their major categories, and it also works well with this category, but particularly in indoor environmental quality, and first category energy. Okay. So passive house, so this is your organization that advocates for buildings that are part of the climate solution, not a problem. So if we can combine passive house, let's combine it with low embodied carbon, plus we electrify everything, and then we'll talk about clean energy. Then that's the holistic approach for climate action for the building sector. Okay, so passive house. So this is what we want to accomplish. So we founded Passive House. We want all Filipino designers and builders to become passive house professional, and we want all future projects, whether new construction or retrofit, to be built to the passive house standard. And we want to advocate that passive house be mandated in tender specifications, policies, and building code. So where are we at right now? So right now, there are zero certified passive house in the Philippines. And a quick look at the passive house database. There are only five known Filipino certified passive house designer, and four of them are members of the board of the passive house. So I hope this webinar will inspire the architects and engineer here to get uh, trained and become a certified passive house designer. And we're also launching the Passive Bahay Trailblazer Challenge. So be part of history by building the Philippines' first passive house certified building. And in return, you'll get a lifetime membership to Passive House Philippines, and you'll be a diamond sponsor for 10 years. And last but not the least, a lifetime acknowledgement as a Passive Bahay Trailblazer in the Passive Philippines history webpage. So I hope you'll take this challenge. Okay, so I'm gonna stop talking. So I'm sure you're all eager to learn how a passive house can be applied in hot and humid climate. We are fortunate to obtain a presentation from the architects of the Sri Lanka passive house, Jordan Parnas of Circular, and Dylan Martello, the energy building consultant for this project.
Hello, my name is Jordan Parnas, and I'm the principal of Circular. We're based in Brooklyn in New York in the United States, and we have a track record of doing sustainable and social justice focused projects across the world. And with me today is Dylan Martello. Dylan, do you want to introduce yourself?
Sure. Thanks, Jordan. My name's Dylan, and I'm with Stephen Winter Associates. I'm a senior building systems consultant, my official title, and we were involved in this project in support of the passive house design approach for this project. So we're based out of the Northeast US, but and like Jordan assisted this project halfway across the world. So we're excited to tell you about it.
Yeah, so we're going to get into the nitty-gritty of the project in a bit. But as a way to sort of kick things off, what I'm going to do is play a brief video, which we made a few years back, which summarized some of the challenges that we faced, and also provides a nice overview of the scope of the project. And just to avoid confusion, our firm was previously known as JPDA. And so we talk about JPDA a few times in the video, and that's actually now you can just understand that as us being circular. So once we play the video, we'll get back to the presentation deck and we'll go through some of the more specifics. So I am going to share my video screen and start playing.
We're here today in Colombo, Sri Lanka, where behind me is one of our most exciting and interesting passive house projects. The Star Garment Product Development Center is a combination office and industrial building where both design, sourcing, pattern making, and sewing happen under one roof.
This project is a model for how businesses can use passive house design principles in any climate and on any building type to significantly save money on energy and operational costs, improve worker productivity, and contribute towards an environmentally and socially conscious future. Passive House is a holistic set of design principles and efficiency standards that strictly regulate the amount of energy a building can use, guaranteeing a very high level of comfort for the people inside. Its basic principles include proper insulation to reduce heat transfer, an airtight enclosure to prevent leakages, high-performance windows and doors, and an energy-efficient heat recovery ventilation system. The Star Garment Building is located in the heart of Sri Lanka, just above the equator, where the climate presents challenges to designing efficient, sustainable, and comfortable buildings. The existing industrial shed was first stripped down to its bare steel skeleton and concrete slab on grade. Modifications were then made to the walls and structure, and the renovation included a high-performance heating, ventilation, and air conditioning system, a complete air barrier, continuous layers of insulation on all sides, high-performance windows and doors, and an insulated roof assembly with solar panels. For the Star Garments project, energy use is projected to drop by 70%, with a 90% reduction in dehumidification energy and a 73% reduction in heat pump energy. The payback period is just 6 years with a 16.6% annual return on investment, saving the company over $50,000 in annual utility expenses. Maintenance expenses are significantly reduced by the high standards of materials and methods of construction. Employees enjoy year-round comfort in a workspace that provides filtered fresh air, abundant natural light, low humidity, and consistent temperatures. Studies by researchers at Harvard University show that employees with access to properly ventilated air boast a 60% better job performance, have 30% fewer headaches and respiratory complaints, and increased alertness due to better sleep at night. At JPDA, we are uniquely qualified in overseeing passive house projects. We stand out for our close collaboration with a team of the world's leading sustainable experts and engineers. Unlike other sustainability standards like LEED, Passive House is evaluated through comprehensive performance testing before and after each project is complete to ensure the building holds up to the highest standards. JPDA was able to use our expertise in Passive House standards on the Star Garment Innovation Center to create a model which can be replicated throughout the world on any building type and in any climate to ensure sustainability, energy efficiency, and high social and ethical standards.
Well, thank you to my team for putting that video together a few years back. It's definitely nice to see how much younger Dylan and I looked back in those days. So I'm going to kick things off now and share the deck. There we go. And yeah, so welcome to everyone who's joining this conference and our presentation. And thank you, Jessica, for your introductory remarks. It's always been a pleasure working with PHI, and we look forward to continuing to have a great relationship as we move forward with new projects. Yeah, so this project was essentially a retrofit, and that's really important to understand. It was not a ground up construction, and that's something that we believe very strongly in, as doing renovations and retrofits is a much more sustainable way of creating space than knocking down and building new buildings everywhere. A brief overview of our firm. As I mentioned before, we're called Circular now. We're based in Brooklyn, New York, and our focus really is on sustainable architecture, interiors, and experience design. We're certified passive house designers, and we're also certified B Corp. We are driven by the pursuit to provide project excellence for both our clients and the common good. And you can visit us at circular.cx. And we have a long list of corporate and institutional and government clients that we've worked with over the years, both in New York and the United States and internationally. And of course, we have Dylan from SWA. Dylan, do you want to tell us a little bit about SWA?
Yeah, absolutely. So, Stephen Winter Associates, we're over 50 years old, and we're an employee-owned company as well, which is exciting. And we have offices across New York, Washington, D.C., Norwalk, Connecticut, and Boston. And my role is on our Passive House team, particularly our high performance building solutions team, which focuses on these deep energy energy savings type projects. And we do all sorts of, anything and everything as it relates to sustainability in buildings. So energy conservation and management, decarb, green building certifications, but we also do accessibility consulting as well. And we believe that's a big part of sustainability. It's not just about energy and comfort. It's also about accessibility and equity. So yeah, excited to fill you in. Thanks, Jordan.
Awesome. Yeah. And I mean, we of course went to Stephen Winter as soon as we got the project because we knew that there would be no better partner to allow us to tackle this challenge and to make the project a success. And we were certainly happy with that decision. But of course, there were more than just Circular and SWA involved with the project. We had a number of local architects and engineers and other consultants who were based in Sri Lanka, as well as subconsultants based here in the United States. And I, always want to reinforce that having a strong team and a team that is closely aligned in terms of goals is critical in achieving these high performance buildings, achieving success, both in terms of maintaining the performance criteria, but also schedule and budget. Everybody has to be drinking the Kool-Aid, everyone has to be sort of on the same page, and everyone has to be fighting for the same thing. And we were really lucky on this project that we had so many amazing people that worked so hard to do something that hadn't been done before. So yeah, as the video kind of begins, we're talking about Sri Lanka. Those of you in the Philippines will be familiar with the climate, but we're just north of the equator in Colombo, and it's a tropical monsoon climate. We have a pretty narrow temperature range across the annual seasons, varying mostly between 27 and 29 degrees. We do get quite a lot of rain at about 2.5 meters of rain annually. And you can see there are sort of two rainy seasons, but I think what's interesting here is that sort of narrow temperature range. And this really is different than a lot of passive house projects that you might see, for example, in the United States or in Europe, where you have a pretty wide temperature swing over the course of the year. And this did present some advantages, which we'll get into a little bit later. So the project site was also interesting for us. It was an industrial park that was adjacent to the airport. And we did have a lot of benefits because it was in a tax-free and duty-free area. And this really simplified bringing in a lot of the specialized materials that were required in order to build the project. We certainly could have done it elsewhere in Sri Lanka, but it would have required a lot more paperwork and a lot more bureaucracy in terms of tariffs and making sure that appropriate duties were paid from the various countries where the materials were sourced. So pre-renovation, this is what we started with. It was an existing factory building, hadn't been used in a few years. It was a very simple two-story, basically a shed. And as we start to look at the context, we can see that there are a few trees around which provide a little bit of shading, but mostly it's very exposed, very open to the sun. And so, really managing that heat and humidity, as Jessica was mentioning in her introduction, was the key sort of factor in terms of creating comfort and determining those performance criteria for the occupants. So on the inside, it was mostly just exposed steel structure. The building itself was divided into 2 floors. And here we are on the lower floor. The upper floor had been designed to be column free, which was really nice because it gave a lot of flexibility in terms of the ultimate layout of the working space in this area. And one of the things that we found interesting as we started the project, and this may not be so unusual in the Philippines, but certainly for us in North America, there was a lot more flexibility in terms of thinking about how some of the different program areas needed to be either in conditioned spaces or could alternately be considered to be almost outside. So whereas in the United States in particular, there's a very hard line between what we consider to be the inside of the building and the outside of the building, in Sri Lanka, just culturally, there is a much more sort of fluid boundary. And so you have a lot of functions like, for example, this washing area, which essentially was more or less outside, protected from the rain, but other than that, with no climate control. And so as we were working through the project and starting to understand, where that boundary of the treated floor area was, it was interesting to discuss how the clients felt that some programs didn't need to be within the treated floor area. And that gave us a little bit of flexibility. So as we move forward in the deck, I'm going to talk a little bit about the design analysis and the feasibility. And so feasibility is of course, not just can we do the project, but also working with the clients, understanding their needs, understanding their budget, their time frame. And as a part of that, a study was done where we looked at the building, the plans that the client had developed for how the building was going to be used, and then worked very closely with Stephen Winter, who actually ran through a preliminary energy model to develop feasibility analysis, both in terms of the financial side of it, in terms of how much money it would cost, but also the potential payback period and a lot of other variables, which were instrumental in convincing the clients to embrace Passive House as the direction to go. So this is a simple cross-section of the building, and here again you can see the upper floor, which is open, has no columns, and you can see that just even in this section, you're starting to see a split between production area, which is in the upper floor, and then more offices and support areas on the lower floors. And then this blue is indicating the conditioned area. And you can see how at the edges of the building on this lower floor, the plans were to pull in that edge of the treated area of the building so that we would have some solar shading and have the ability to potentially have less heat loads on some of those lower floor areas. As we look at the building plans, we can see that the lower floor area, as I mentioned before, has a lot of offices and workstations, has lounges, a garment library and fabric library, and of course, security check-ins and some bathrooms. And you can see there's an interesting split between some of these elements which are not in blue, which would be considered to be outside of the treated floor area, like the canteen, for example, and then a lot of these interior spaces, which are treated floor area. As we go to the upper floor, you can see most of the footprint now is considered as treated floor area. And you can see the layout for the production area with the sewing machines, cutting tables, and the other components of the production facility. So, what was our approach in terms of understanding how we might bring this project through to fruition? Well, we had to identify the challenges. And so some of the challenges that came up immediately were that there was not a lot of data, not a lot of information on the existing building. So in order to do a feasibility study and to properly understand how we're going to establish a baseline for performance, it's really important to understand how the existing building performs, what it's made of, how it historically has been used. So we had to do a little bit of digging to get some of that information in terms of the historical primary energy use, and also start to think about how the building energy use would be different from the industrial process loads. So the heavy machinery, the sewing machines, the fusing, all of that, how we could start to understand that differently from the base building infrastructure, the cooling, the lighting, water heating, all of that. We knew up front that there was not going to be a convenient local distributor for passive house equipment or materials. We're very lucky, particularly in New York, that we have all of this sort of right at our fingertips mostly. And we knew as well that this building would not be a simple factory that would be open from, for example, 8 a.m. till 4 p.m. This was going to be a building that would be used very intensely at certain times, and then maybe less intensely for a few weeks, and then ramp up again. And so we need to understand those occupancy and usage patterns to better predict how much energy would be used on a typical basis. In terms of performance goals, we knew right away that EnerFit was the standard that we were going to be seeking. EnerFit is designed for the retrofit of existing buildings. It is slightly more lenient than doing a traditional ground up passive house building, but certainly much higher performance than a standard non-high performance building. And then finally, the cultural and aesthetic goals. I've already talked about that mix of treated and untreated interior and exterior program areas. Keeping the look of an exposed steel structure was very important to the local architect and designer as well as the client. And so a lot of our detailing, a lot of our approach to creating these high performance details was very directed to maintaining that look of an exposed steel structure. And then ultimately, sort of big picture, we had this goal of creating a regional model that could be used and understood to showcase the fact that this technology, that this approach could easily be replicated by other teams, both in Sri Lanka as well as regionally. We really wanted this to be a showcase to show people that you didn't need a crazy budget. You didn't need a crazy client. This kind of high performance passive house standard building could become a common and conventional model for future development. So the initial studies showed that there would be a relatively quick payback period, around the order of 6 to 7 years. And so this was enough to convince the clients that they were going to move forward with the project. I'm going to hand it over to Dylan now. That's going to talk a little bit about some of the nuts and bolts of how we did that engineering to reach those performance targets. So Dylan, just let me know when you want me to move forward.
Sounds good. Thanks, Jordan. So this project, as you can imagine, is very unique in its the utilization of the building and its location as it relates to where passive house really started its roots in Europe and more conventionally, I think passive house is generally associated with heating dominated climates, or at least climates that have a heating load. And obviously this building, as Jordan mentioned, I don't think the temperature drops below 68 degrees Fahrenheit all year. So which would be about 25 degrees Fahrenheit Celsius. So as you can see, there's really no heating demand or heating load. All of this building in terms of its load and energy uses as it pertains to space heating and space cooling is all just for cooling and dehumidification. And this was a pilot project with the Passive House Institute, given this unique aspect of it. So there was a couple of things that we worked very closely with Passive House Institute on to ensure that the model was refined in a way that accurately represented energy use in the building, and we'll get into that in a bit. But as you can see, the criteria and the thresholds, if you're familiar with the more conventional passive house metrics are just very large numbers, and that's just because of the unique climate and the unique utilization of this building. And for this specific project, we needed to meet the cooling load threshold under the alternative criteria there of 20.83. So that was sort of our critical point here. As far as the process for modeling a building like this, as it relates to passive house, you may be wondering, is it different with a building in this climate? How different may it be? It's actually not that different. The design principles are very much the same, just applied with the cooling mindset in mind, and also with the mindset of controlling internal loads. That's a big part of the load profile of this building. But the process for doing passive house and showing compliance is really the same in that we're modeling the building's geometry. We're accounting for the nearby shading elements around the building and the shading elements on the building itself. We're doing thermal bridge modeling. We're doing detailed plug load accounting for a building like this, and that all gets modeled in the PHPP, which is what you're looking at here. This is the verification page of the PHPP.
Dylan, maybe it's
how we-
worth, because I'm not sure how familiar people are with PHPP, maybe
Yeah.
just to give them a super brief introduction as to what it is.
Absolutely. So the PHPP stands for the Passive House Planning Package, and it's actually just a big Excel spreadsheet. So if you're familiar with Microsoft Excel, it's easy to kind of get up to speed, but it's a whole building energy model. So basically what this means is we input various aspects of the building's geometry, its envelope assemblies, everything about the building that could impact energy performance. Essentially, we input that into this model, and what we get in return from this model is what you're looking at here are results that say, here is what the building's cooling demand and dehumidification demand, and that's 183 kilowatt hours per meter square per year. And then the cooling load, and you can go down the list and see these results here in green cells. And then we cross-check that against the criteria that's in the passive house standard, and that's embedded within the PHPP. So it's an easy to use tool to model the energy use in buildings, and it's in Excel, which makes it, I think, much more applicable, or much more accessible for use than, say, other energy modeling softwares that are out there. It's meant to be simple enough for anyone in our industry that is familiar with how to use Microsoft Excel to use. And you have to know how to use it and use it appropriately, but it's really a great tool to use. Okay, next slide. So as Jordan had mentioned at the start, there's very specific load profiles in this building. It's a very unique in regards to how energy is consumed in this building. And what you're looking at here is a pie chart breaking down the different end uses. So cooling active just really is referring to the cooling energy use to maintain adequate temperature in the building. And then you can see a smaller slice of the pie for dehumidification. I'm going to put a caveat on this because that number for cooling dehumidification could have been a lot higher, and we're going to explain why in a little bit. But you can see that the cooling energy use for the building, which is both cooling the temperature but also dehumidifying the building, is over about 34 to 35% of the building. So that's cooling is the biggest chunk. But the next biggest chunks are internal loads. And these are process loads for sewing equipment. So when we say the term process load, really what that means is it's a unique energy load to a building that's not typical. And it's unique in regards to how the building is utilized. What is its actual function? And in this case, the function of the building in a large part was to make and demonstrate actual articles of clothing. So there was a lot of equipment, like sewing machines being the biggest one, but other things. I've learned so much about how clothes are manufactured through this process. And in fact, one of the, I think, most helpful um, things that we did in our process and our involvement with this project was myself, my colleague Lois, and Jordan and his team went out. This was one occasion of multiple, and I know Jordan and your team, you went out more than we did, but one of our trips out to Sri Lanka, we actually went to a neighboring building within this facility and observed how often the workers were actually putting their foot down on the pedals, which spun the motor in the sewing machine. And the reason we were doing that is because we really wanted to try to get an accurate prediction of energy use from this equipment. And while you can get a wattage or a power draw from a piece of equipment like a sewing machine, that doesn't tell you how often it's used and how often it's running at that power draw. So we really had to hone in on how often is that motor running. And what we determined was that it was like over about a minute and a half sample size that we took. And we did this multiple times. I think the motor was actually running for about 15 seconds, or like, 15%, more or less of the actual time that we sampled. So that helped us define our assumptions for how often this equipment was running at that power load. And once we did all that, what we've ultimately arrived at was that the overall energy use for the sewing equipment itself was about 20% of the overall building's energy use in our model. So that's a big chunk. The other big chunks are lighting, as you see here. The lighting is important given the utilization of the space. It needs to be adequately lit, and then office equipment as well.
And I just want to jump in for a second because I think it's really important to underline, sort of how Dylan was talking about this process. A lot of our approach to this project overall was pretty low tech, right? I mean, just like going into a neighboring facility and watching how the workers were actually using machinery. It's not about a lot of complex calculations, but literally just looking at how they're using the equipment, how often it's used, so that we can get as accurate a sense of the real energy loads going to be used in the building. And so, a lot of this requires, rolling up your sleeves and just being prepared to invest a certain amount of time, but it's not particularly difficult and it's not particularly challenging, but it just requires that sort of level of commitment to really understanding your client's needs, understanding how the building is going to be used in order to make sure that you're, on the right track.
Yeah, absolutely. Okay, next slide. So the dehumidification load that I was referring to earlier. So this is, quite literally, this is the load, the energy use that's required to basically take the water vapor in the air that makes it humid and squeegee that out and get it out of the building. So it helps keep it dry in there. And this is huge, not just from an energy use standpoint, but it's huge from a comfort perspective. Passive House is so, driven not just by energy performance, but also by high levels of comfort. And really this facility is, really created an extremely comfortable environment compared to what the typical conditions are. And there's many aspects of comfort. We could talk about like acoustics, but we'll save that. But humidity is a big part. I mean, I'm sure we're all familiar with the feeling of it being hot and humid and muggy and just it's oppressive and you just want it to be drier. So it was a big load. And one of the things that we looked at for this project early in design was a solar charged desiccant dehumidification system. Some big words there. But basically what that means is you have a solar thermal array, and that's what you're looking at here. This is a plan view of the roof, and the more lighter bluer colors there, those are the solar, what we propose as a solar thermal array for the project. And we arrived at this number based on how this system actually works. So I'm going to explain that here in a second. So basically, what happens is you're utilizing heat um, to essentially heat up a material that we call a desiccant that absorbs moisture and helps bring moisture out of the air. And you could essentially these systems they will do this process with either typically with like a natural gas fired heater, or in this case on this project there was no connection for natural gas. It was all electric, so we would have had to rely on an electric based water heating system that was supplemented by this solar thermal array in order to meet the loads in the building. And essentially what we determined at this stage was that Not only is this system, I think novel in its sense, and it's unique and may add some complications to the project. It also just was likely going to result still in a high energy load because of the fact that it's really a solar assisted desiccant-based dehumidification system. In this case, we would have had to rely on electric water heaters to help bring that water up to an adequate temperature to actually sort of make this desiccant evaporative cooling process happen. And that temperature for the water needed to be about 180 degrees Fahrenheit, which is about 82 degrees Celsius. So you needed to get really hot water. And we were concerned with the fact that that might end up just resulting in a lot of energy use as is. So next slide.
Yeah. So just to underline this, we didn't use this system. This
Right,
was
true,
something
yeah,
that
good
was
point.
that was looked at, but we actually did not end up with this sort of slightly nutty system in our project.
Exactly. So if you go to the next slide, so the actually more conventional based approach in this part of the world um, is to just use electric resistance reheat, and that's what these VAV or variable air volume boxes that are shown here in this floor plan are representing, and that is just a straight up large energy consumer, just like I described in the solar charged desiccant system. We were concerned with the energy loads, with electric resistance being our form of reheat. Now, let me just quickly explain the concept of reheat, because some of you may be asking, why are we heating anything? We're trying to cool air, right? So the reason we have to do this is because in order to get moisture and water vapor out of the air, you not only have to cool that air's temperature down, but you actually cool the air's temperature down to a even lower temperature that it will ultimately end up being when it's just has gone through the cooling process. So as an example, I'm going to use Fahrenheit here because those numbers are more familiar to me, but you may have, let's say, 80-degree Fahrenheit air that gets cooled, and you want that air to be, let's say, 70 degrees Fahrenheit. You not only cool down to 70 degrees Fahrenheit, you're actually cooling that air down to about 50 or 55 degrees Fahrenheit. And what that does is, by cooling it to that low of a temperature, you're creating condensation, and that's what's wringing the moisture out of the air. And then you drain that moisture from the building with a condensate sort of drain process. But that air is really cold. It's 55 degrees Fahrenheit. This is where the reheat comes in. And essentially, if you're reheating with electric resistance, you're wasting a lot of energy that you could have essentially used because you have so much heat in the building already. How do is there a way you can use that heat as opposed to having to make heat with electricity to reheat that air? So we quickly flagged this and said, this is going to use a lot of energy. We need to evaluate other options. So we did not go with this approach. Next slide, please. So what we ultimately landed on was what are called heat pipes with heat recovery. And this is a very simple, novel, elegant solution. What it is it says, okay, before we take that air that's in the building that's warm, let's say it's 80 degrees Fahrenheit, we're going to run that heat over a pipe or a series of pipes, and these are called heat pipes. And that heat will essentially heat a fluid within the heat pipe itself, and that fluid gets basically wrapped around the main cooling coils in the primary air handlers in the building, which is what this diagram is showing. And that heat that started off before the cooling coil, and now we're taking it and moving it over here, is the heat that will reheat that super cooled air. So instead of using an electric resistance heater that will use a lot of electricity, a lot of kilowatt hours, you're actually getting this reheat essentially for free, which is really an incredible concept, but it works extremely well. And in this case, it was a great fit for this project. So if you go to the next slide, we have a good diagram here to really kind of show that this is from the specification of the unit. And you can see, again, in degrees Fahrenheit, but you can see that air starts out at 95 degrees Fahrenheit, and then it actually sort of gets like pre-cooled by taking some of that heat and sending it to the reheat section of the unit. and that air drops down to 82 degrees Fahrenheit. Then it gets super cool down to 52 degrees Fahrenheit. And then that heat that that free heat that we stole from our air in the building brings that air back up to about 65 degrees Fahrenheit. And that's very comfortable because it's also very dehumidified. It's not a very humid air. And that 65 degrees Fahrenheit is, you know, a very comfortable condition. Okay, next slide. So what does this mean for energy savings? Well, significant. If you can see the PER demand, or primary energy renewables, this is like a source energy use for the building. If you're familiar with source energy, or it's really a way to measure whole building energy use in passive house buildings. You can see that was reduced by approximately 20%. Almost a quarter of the building's overall source energy use was saved just by making this change to the reheat system. So huge savings. It was almost 110,000 kilowatt hours per year of energy savings, which if you were to sort of translate that into US dollars, which is where we operate, you know, that's about $20,000 to $25,000 per year in USD. That's significant, and that's what helped make this project not only energy efficient, but helped make it pay back, and from what Jordan was saying, have actual good return on investment. Okay, next slide.
All right, so I'm going to jump in and talk a little bit about how, you know, from a design perspective, we approached some of these sort of tricky challenges. And I just want to give you again kind of a quick overview of some of the strategies that we employed. You know, some of these were very specific to this actual building, but of course the overall general concept is always going to be the same on a passive house project. And so on a passive house project, you're always going to be working with continuous insulation. And in this case, it's indicated by this yellow line that sort of wraps around the building. You're also going to have continuous air barrier that's wrapping around within the insulation. We're using energy recovery ventilation, which is a way to bring in fresh air, but capture, in this case, the cooling energy that's already in the air within the building. And also some more sort of quote unquote passive strategies like solar shading to reduce the amount of solar heat gain that's coming in from the perimeter windows, and then some basic strategies like reflective roof paint. But if you've ever seen some of the sort of standard passive house diagrams, you know, this building obviously is kind of bigger and wider and has some unusual conditions, but it's essentially the same diagram you're always going to see, which is basically, you know, use your finger to trace the line of insulation, use your finger to trace the line of air barrier, and then show how your ventilation strategy is working, show how you're using high performing windows and doors, you know, show how you're essentially doing whatever you can to take all of that precious treated air that you've created within the building, keep it within the building, but bring in fresh air so that you have very high quality air. And so, you know, as I mentioned here, we had those exterior shading devices, which you saw in the videos, which were literally just very low-tech perforated metal screens outside of the windows. There was reflective roof paint to just bounce the sun off. And then, as I mentioned before, the lower level was actually pulled in at the perimeter, and that created these cantilevers so there would be shading for those lower level areas. The client was interested in having some renewables on site, so we had some PV arrays on the roof, but you know, those are not required for passive house. It's really mostly about preserving and maintaining the energy that you've got within the building. On a conventional passive house project in North America or in Northern Europe, you'd be very concerned with having tons and tons of insulation. You know, here, of course, we did have some insulation, but it was much less than you might have in a climate where there would be a much bigger temperature differential between the inside and the outside. The continuous air barrier is all about making sure that none of that precious air is leaking out. So it's not leaking out at the windows, it's not leaking out at the doors, it's not leaking out where your floor meets your ceiling, it's not, or your walls rather. And we'll talk a little bit about some of the challenges of ensuring that we had that air barrier in a retrofit scenario when we talk about some of the construction administration that we did. So for cooling and dehumidification, Dylan already went through the sort of magic of the wraparound heat pipe for dehumidification. We were using a VRF system for cooling. And of course, the energy recovery ventilation means that we're able to bring in lots and lots of fresh air while maintaining, around 90% of efficiency. So that means that the cool air that's coming out of the building, that cooling is actually transferred at a very high level to the warmer air that would be coming into the building to provide fresh air. And so, again, knowing that this project was going to be a pioneer, in a country that had never done a high performance building before, we really wanted to keep the methodology and the materials as simple and as low tech as possible. So here you see a mock-up that was created on site to demonstrate some of the different layers. And essentially what we're working with is what's known as an EFIS system. So it's essentially exterior insulation with foam insulation with a stucco layer on top. And here you can see some of the layers of that coating and the insulation. But of course, some of the magic of Passive House comes down to some of these special products like the sealant tapes that are used to ensure that there's no leakage of air between the joints of materials. We also used a liquid applied air barrier on this project, and we'll talk about that more in a little bit. But at the end of the day, in terms of a high performance building, this is about as simple as you can get. It's really some basic materials coming together in a very simple way that didn't require a lot of specialized labor or specialized training in terms of how to put it all together on site. So I mentioned before there were some specialized material. Tape is one of the number one things that you'll see on a high performance building project. It just works so well at joining things together. The tapes last for upwards of 100 years. So it's not a question of having to go back and replace it almost ever. And then here we had a couple of, fairly exotic products that we actually haven't used very much since this project. We had a spray-on thermal bridge mitigation coating, which was literally kind of like a paint that we painted on, where we had some different pieces of steel that were coming in from the outside of the envelope, meeting the interior steel structure as a way to mitigate some of that thermal bridging. In other words, trying to prevent that warm temperature from outside coming into the inside of the building. We had some polyurethane structural blocks. And this was essentially, again, a way to isolate some of those exterior members of the building and keep that heat from sort of channeling in. In a cold climate, it would be doing the opposite. It would be keeping the outside cold from actually working its way into the building structural frame. And then our roof was a foam sandwich panel, which worked as a sort of prefabricated element that both provided weather tightness, but was also very thermally performant for the needs that we had. But pretty low tech, but specialized when used in the correct way. Windows were definitely an area that we spent a lot of time thinking about. It's challenging often to sort of come up with these details when there are a lot of unknown conditions in an older existing building. A lot of the details that we planned prior to demolition had to get revised as the real conditions were exposed after demolition, and even as things were adjusted during construction. So this was a little mock-up that we made in our office, just again showing the different layers of materials and trying to explain the sequence of installation for the contractor. And so, one of my recommendations is always, not only have everybody on the team, excited and bought into the goal, but also really provide as many simple sort of hands-on tactile materials as you can, so people understand, what the end result is supposed to be. And so this is just a way that, anybody can make a basic mock-up out of materials that are on hand, just to show how everything should come together and help to eliminate errors on site. There was, of course, a lot of specific detailing. And so this is just a selection of some of the specific details that we developed. Here you can see in some of these sections, we had some interesting conditions. I mentioned before how we had this sort of cantilever condition where on the lower level, the thermal envelope was actually pulled back. So these columns were exposed. So some of these columns were wrapped in insulation, but done in a way and finished in a way that they still read as kind of a chunky steel structure. But you can see what's critical here is that our air barrier, which is represented in the blue, is still wrapping continuously around all of those areas. So there's never a situation where, for example, we're going to have an air barrier just on the wall, but not, above and below a treated internal area. These green areas, that's where we applied that thermal bridge mitigating paint called Aerolon. The client was so excited about it that we had originally planned for it to be painted over, and they actually left it exposed because they love telling the story about how that material was used in the building. But different conditions. Here, for example, we had an opening in a masonry wall, and we'll talk a little bit about how masonry was a really big part of this project, which was unusual for us. In North America, masonry is generally used as a decorative element, but again, trying to work with the most familiar and comfortable materials that the local builders had laborers that knew how to work with. It quickly became apparent that masonry was going to be the primary infill material for this project. So not only at the exterior where we didn't have glass, but even for interior partitions. And I'm not sure this may be the case in the Philippines as well, but obviously masonry is a very low-tech, system that's been around for thousands and thousands of years. So our approach was not to say, oh, don't use masonry, that's crazy. Our approach was to say, okay, let's use masonry and let's figure out how to make it work. So we built on the masonry with the liquid applied air barrier and the insulation, and that actually ended up working out very, very well as a very low-tech way of satisfying the performance requirements for the building, but still allowing the builder to use the techniques and staff that they would use in a conventional projects. Of course, there were some more complicated details at sort of window and slab connections, as you would have in any sort of modern building. And you can see, we sort of very patiently detailed all of the different layers. And of course, a lot of this got changed up in the field. But the important thing was to really demonstrate how the insulation would be continuous, how the air barrier would be continuous, and how we would be wrapping these layers around these sort of transition points. And the same thing at the ground. It's very common in a passive house building, if you're building from scratch, to actually insulate underneath the ground slab. In this building, we were not about to rip up the existing ground slab, but we did extend the insulation down, a good, I would say at least a meter below the ground plane in order to really retain that cooling within the building and not allow it to be sort of sucked out through the foundation. The roof as well, we had some pretty complex intersections here because we were working around an existing steel structure. Dylan will tell you a little bit about how that was almost our downfall. But here you can see a condition, which is a little bit hard to read in this drawing, but you have our new roof assembly with the foam. We have our existing steel frame. We have these purlins, which are actually extending outside of the interior of the building. We have our insulation. And again, just showing how the insulation is continuous, the air barrier is continuous, and then, some Aerolon spray to sort of cross our fingers and hope that the thermal bridge mitigation would be as efficient as possible. And, theoretically, it all should have worked perfectly. So construction, this is where obviously, all of our theories, all of our energy models, all of that is sort of put to the test. So what did it look like? Well, the beginning of the project was some selective demolition. We knew we wanted to retain as much of the building as possible. So what that meant was we had to get rid of those things that we couldn't reuse. We couldn't reuse the existing roof. We couldn't reuse the existing exterior cladding. So those things were removed. There were a few small areas of the structure that were removed as well. And once that had been completed, almost immediately the first thing to do was to put on the new roof, and you can start to see this new insulated roofing going up. It went up very, very quickly. Those panels are basically just drilled in place, and it's very efficient and very easy to do. New steel was added to extend one side of the building because there was a specific configuration they wanted with the floor plan. And so you can see how this new steel frame is being integrated with the existing steel frame, and you can see our new roof onto the right and some of those new structural elements for the roofing as well. We talked a little bit about that Airlon liquid thermal break mitigation. So here you can see it as applied. It's yellow. It stands out. It's very visual. We really liked on this project that each of the layers of the air barrier and the insulation and the thermal bridge mitigation, they were actually very easy to see in the field. So it was very easy to do that sort of visual check to make sure that they had been applied in the right places and they were there. And again, when you're thinking about how to detail these kinds of projects, my advice is always to keep it as simple as possible, allow for as much visual clarity as possible so that just a casual walk around the building will reveal if there's, any obvious issues, and to try and work with the local expertise in terms of materials, in terms of fabrication, as much as possible. And that was definitely our approach. Here again, one of those polyurethane insulation blocks, in this case, separating this outrigger steel beam from the primary steel structure. And this is basically just a big piece of insulation that's very, very rigid. So it has a structural property, and you're literally just sliding it in between two components to prevent this exterior member from channeling in that either warm or cold temperatures into the primary steel frame. So here we can see some of that masonry starting to go in. And again, this is not at all how this would have been done in North America or probably most parts of Europe as well. But it was very easy and simple for this construction, for this project. And so we were happy to run with it. And it ended up being a great solution for keeping things moving quickly, using local materials, and really avoiding waste as well. So the liquid applied air barrier that I'd mentioned before, this was applied directly to the masonry surface. So the air barrier is a critical part of any passive house project. As I mentioned, you're keeping that precious treated air inside of your building. And there's many different ways to do air barriers. But for this project, because we were doing masonry, having an air barrier that could literally just be painted on and was very visually easy to inspect proved to be the simplest and most straightforward way of achieving this critical function. On top of the air barrier, you're starting to see some of that exterior insulation. So you can see there's that layer of the masonry with the stucco. You can see adjacent to it a part that has the air barrier applied. And then on top of that, you can see the insulation. So very much like that mock-up that we showed you earlier on, it's a very simple and straightforward series of steps to apply one layer on top of the other. It requires very little in terms of specialized skills. It's very easy to check visually that it's been done properly, and again, was critical to the success of this project. I mentioned as well that we have these overhangs. Here you can see that insulation wrapping underneath. And again, this whole idea of continuity, of having a continuous insulation, continuous air barrier. You're not just thinking about the building as something that has a roof and sides, but it's got undersides as well. And particularly in this building where we had these overhangs, it was really, really critical to make sure that we properly treated them so that they would, keep in our air and not allow for thermal bridging. And then the final layer on top of the foam is the EIFS stucco. So this becomes a protective layer Stucco again is a very low tech and simple surface treatment to apply, and it was a great choice for this project. Now we get into some of the more complicated details. This here is starting to see the glazing framing going in. So we've got our steel frame, we've got a little bit of insulation, and we've got a little bit of kind of build out to create that frame that the glass is going to be sitting in. We spent a lot of time, evaluating different glazing systems. One of the nice things about this project was because of that sort of small temperature differential between interior and exterior, we didn't need a super high performance triple pane glazing system like you might find in North America or Europe. So we were able to use just a reasonably good double pane system, which was produced in India, and so didn't have to travel very far and was fairly easy to get and in theory to install. So I'm going to hand it over to Dylan now, who's going to talk a little bit about some of the QA and QC that happened during the construction phase. But this is a photo of one of those trips where we arrived in Colombo, and the mission was going to be to test one of the first panels of glass that had been installed and make sure that it had been done properly. And so, Dylan, I'll hand it over to you.
Yeah. So, we've got a lot of experience at SWA working on a lot of different passive house projects, a lot of working directly with contractors, directly with the builders, and really, and directly with design teams, just as we did with this building. And one thing I always say is the devil is truly in the details when it comes to passive house. And what I mean by that is the construction documents or the drawings, and we're looking at some details here as an example, really need to be well documented. They need to show not only where the insulation is and how that prevents thermal bridging and all of the things that Jordan mentioned, but also is very clear about how that air barrier is maintained at all locations. No matter where we are in the building, we need to know exactly how the air barrier is continuous, whether it be the fluid applied membrane, the air barrier tapes that we showed earlier, or any sort of other product that might act as our air barrier. So the devil truly is in the details, but it's also very much related to the contractor's understanding of the details and how they need to be executed and built on site. They need to understand exactly why the stuff is in place and how to do it properly. So we have checklists that we make for them, and we do this on every project, and we did it for this project where we develop both typical inspection checklists, which we're looking at here are like some of the more typical conditions and details throughout the building or locations, and how those are dealt. So in this case, we say, here's the item to be inspected. Here's how we're going to inspect it, or whether it be a test that we do to verify air leakage is meeting our metric, or just a visual inspection. And we have that detail snipped in here just so that way the contractor is completely aware and on the same page of how these specific locations need to be dealt with. You go to the next slide. We also have unique conditions as well. So a separate checklist for like one-off areas around the building. We might have a unique wall type. So like that first detail, for example, is showing one of those new masonry conditions with the ephes on the outside there to the right of that, and how that interfaces with sort of a floor condition above. That's a unique location, and we want to make sure that the contractor is aware of exactly how to deal with the air barrier and insulation at those locations. So that's what this is meant to do. So we developed these checklists before the project went into construction, shared those with the team, walked through them, allowed for opportunity to ask questions. This is a great opportunity, and really this should be done even earlier, as early as you can, really, to discuss questions of constructability. So basically, you can draw all you want on the paper in terms of how the detail needs to be executed, but really the contractor needs to confirm that they can actually build that they can actually access with their hands or with the caulk gun or whatever it might be to execute that detail. A constructability review is critical, and that's what these checklists are there to do also, is to help ensure that everything that's being drawn is actually buildable. Okay, next slide. So the other big aspect of QA/QC during construction is doing actual testing. So this is testing that's not necessarily, I'd say, required to show compliance with the standard, but it's testing that we know is needed to ensure that the quality of construction is up to the level it needs to be, to make sure that the building will pass the whole building blower door test when the building's complete. So you have to keep in mind, when we do a whole building blower door test at the end of construction, most of, if not all of the finishes on the building will already be up, which means we don't really have access to go in and find leaks and seal them and address problems. We did have a specific situation that I'll get into in a minute that we dealt with when we did the whole building blower door test. But as far as your primary areas of your envelope in your building, like walls, roof, windows is the main areas, we do this intermediate testing, particularly at windows, because that's usually where leakage problems can really arise as most frequently. So what you're looking at here is one of these intermediate quality control tests. So what we do is we have a little tiny fan, and that's that black cylinder there in that photo, and hook it up to a flex duct tube that connects to basically a plastic shroud that creates a chamber, an air chamber. And we pressurize and depressurize that chamber to not only measure how much air is flowing through the assembly, and we check that against what we expect or are hoping to see to meet these passive house targets. But in addition to knowing the number and the airflow, we also inject some theatrical smoke, theatrical fog into that chamber. And we can either push that air or pull it to see where fog may be coming out from the other side. And that helps us identify what areas may be leaking. So a good example of this with windows, for example, especially windows that are operable, are at corners. So where you don't have maybe as strong of an engagement of the gaskets that create the air seal, if that seal is not great, what you'll see is fog coming out of those corners. And that's basically what we're doing here, is we're creating that chamber so we can pump fog into it and see where leaks may be. Now this actually came, you can go to the next slide. This was a big, really a critical test for us on this project because we did find a key leakage area point. What you're looking at is a very specific location, but if we didn't find this and address this, we might have had real challenges meeting the, I mean, I don't think we would have met the whole building blower door test requirements for the project. So this was critical. And we did this in the middle of construction. And what we found was that there was a specific area within the Windows system that was a very, it was an area where you had many different components coming together and meeting at one like three-dimensional point. And it wasn't very obvious when looking at drawings or shop drawings that this was going to be a problem. And what we found was that this is where a leak was coming out. And it was actually an issue, not just at one specific location, but we found it at multiple locations. So we knew this, we had to address this. So that was ultimately dealt with. I believe we used, I think we used some caulk there to just goop into that location. Correct me if I'm wrong, Jordan, is that right?
Yeah, it was just really tough for them to get their hands in there,
Right.
and it was not immediately obvious visually because you couldn't really see into that spot unless you really, really were looking. And so, yeah, that, as Dylan was saying, that testing was so critical in finding this connection point that, obviously we had drawn it in a few different ways, but until you're actually in the field and understanding how hard it is to get into that area with your hands and everything, I think we used a combination of caulk and then some guidance in terms of, because most of the windows had not yet gone in, so we were able to give them more guidance in terms of how to use the tape and how to avoid damaging that connection.
Yeah, absolutely. So that was sealed, and the good thing about doing this test when we did it was that we were able to work with the contractor to ensure that this got done everywhere on all of the windows before they were finished. So huge importance on this project. Next slide. So sort of fast forwarding to the end of construction here. With any passive house project, you have to verify air tightness in the entire building with a whole building blower door test. So we had to do that here. There was no exception because this was in Sri Lanka or halfway across the world. We had to figure out a way to get testing equipment there. And what actually was maybe one of the most challenging parts of the project, was just figuring out logistically how to ship equipment from America to Sri Lanka. We did look into options for blower door testing equipment in other areas around Sri Lanka, but like Australia and even Europe, but it was just way, way, way too expensive. It was cost prohibitive. It was not doable from a cost standpoint to actually just take equipment from different areas of the world. So we had to ship it. We became oddly experts in international shipping of equipment like this. And this is some of my favorite photos from the project, is our testing equipment in a tuk-tuk this vehicle that's very common in Sri Lanka. Yeah, just in general, this process was just a totally new experience. So, as you're considering Passive House and the growth of Passive House in the Philippines, the equipment is obviously a big part of that. So, uh, yeah, it's something that as you start to have growth of Passive House in the industry, ideally you get more testing agencies, testing equipment in the actual region, so that way you don't have to rely on this costly international shipping to get
The
this.
first project's hard. And once you have that equipment in the country, second project's a lot easier.
Exactly. So this is a snapshot of one of these blower doors. This is actually a smaller fan, so this is what we call a duct blaster, and this was when we were actually on site doing one of the intermediate tests. But the concept's the same. You basically have this door frame that goes into an opening, and you put this big red shroud over it so you're not losing air through it. You stick some fans in those shrouds, and you're pumping air in and out of the building. And it's quite amazing how much little air these buildings leak, and this building is certainly no exception to that. This building was very airtight when we were done with testing. So if you go to the next slide, we have a specific area. So when we did the whole building blower door test, the way the process, I'd say, usually works out is, if we're doing the blower door test, we're the testing agency. We'll set up all of our equipment, and then we'll turn the fans on. We'll build pressure to our pressure differential that we need to meet for the buildings for the test. And when we get to pressure, we sort of do a check to see, okay, do we feel like we're going to pass, or are we failing? Are we over the limit? Before you actually go through and execute the test, which requires very technical steps, we just do a very preliminary test to see where we're at. So we did that preliminary test, and we were actually um, somewhat over, well, I mean, we were over the EnerFit threshold of 1 air change per hour. We might have been around 1.1 or 1.2, if I recall correctly. So we were not passing with the initial test, but we were close enough that we knew it had to be something that we could find to get them under. And what we turned into were a bunch of investigative workers looking for air leaks around the building. So we had the fans running, and we were going around with our hands trying to feel air coming in at specific locations. And we found some stuff that were helpful. It was helpful to find some window gasketing issues that we were able to find and address, which was good. But the key area was these purlin locations. So these photos are hard to tell exactly where they are in the grand scheme of the building, but they're actually on the second floor. I believe there was about 20 or 30 of these specific instances, and they were where the metal cross C channel or purlin penetrated the exterior insulation layer, and you can actually see some of that Airlon paint, that thermal bridging paint, thermal bridge prevention paint that Jordan was referring to earlier in there. And that location was about 13 or 15 feet. So what's that, about 5 meters up? So we couldn't really see this with our naked eye. We had to get up on a ladder. And once we got up on a ladder and started looking, and we were like blasted by air coming in. And we were like, oh, we found it. And then, and not only was just that one location, it was about 25 of those. So that actually is the best possible thing that can happen when you're in that situation, is because you're finding the leaks. That's a good thing. And then we address them. So you're seeing here on the left was before we actually sealed those conditions. On the right is the sealed condition. So in this case, they used spray foam to seal that location, and that reduced the air leakage by about anywhere from 85 to 99% at these locations. So it smashed that air leakage away.
And I will say that it was
Fast.
it was quite a challenge to find spray foam on a holiday weekend in
Yeah.
Sri Lanka, but we did it. And yeah, kudos to Dylan and his team for really going the extra mile and you know, finding these spots and then figuring out how to quickly solve this.
Yeah, and you know, one last thing I'll say, just on that note is there was incredible buy-in from the local builder team, the local building team. You know, some of the nicest people I've ever met, and it was just such a rewarding experience. But as Jordan mentioned, it was a holiday when we were doing this test, and when it's a holiday in Sri Lanka, it's hard to get anyone to do anything that's not related to that holiday or do anything work related. But we had some folks come in and help us out. Particularly the envelope contractor to come out and help address these areas. So it was a huge help from the locals as well to help get to this point. And ultimately after this was all said and done, after extending our stay for a couple extra days, the building passed with a whole building air change rate of about 0.8 ACH 50, which is just absolutely incredible, you know, given all the circumstances, and just a huge accomplishment across the board. So totally rewarding.
So just to kind of give you a couple of, well, a few completion photos to see how it all ended up. So you can see just from a kind of design perspective, how we were able to maintain a lot of that vocabulary of the exposed steel that the client and the local designer wanted. You can see some of the solar shading that we had talked about with the perforated metal screens. And you can obviously see, you know, the new roof and all the glazings. There was a lot of glazing in this project. You can see the building in relationship to some of the other buildings nearby on the site. The local architect was really great in terms of running with some of these concepts and coming up with some great color ideas and some other things to really sort of give some energy and spirit to the overall design. You can see how our EFIS system is wrapping around a bunch of these exposed columns. And then as we look from sort of a higher vantage point, you can see some of the PV arrays on the roof. There's plenty of room for them to install more if they decide to go further in that direction with on-site energy. But for the moment, they were just providing a very small portion of the overall energy load. And then again, just some additional photos showing some of these sort of complex conditions we had. You can see that airline, which is still exposed on the outside as well as the inside. The client was in love with that concept. And here you can see the sort of back of the building, which is actually the main entry point for most of the garment workers. And they would go in through these doors, which are just past this corner. But you can see this large masonry wall, which we had seen previously in some of the construction photos. And here it's got that final EFIS stucco coat on top of the insulation, on top of the air barrier. On the inside, it's really, the nicest, quietest, most comfortable factory you've ever been in your entire life. The air is very clean because of all the filtration, and there's tons and tons of fresh air. It's very actually quiet. Certainly, Colombo is not a quiet city, and this is true for a lot of South Asia and Southeast Asia. You have the noise of motorcycles and trucks and dogs and horns, and the air barrier and the window performance goes a long way to filtering a lot of that out. We have incredible amounts of natural daylight, even though we've really reduced the solar heat gain with the shading. And it's just a really, really pleasant place to work. And, it was great to, walk around and talk to some of the staff when we were taking photos and shooting the video, and really just see how everybody was so enthusiastic to be working in this facility. And, at the end of the day, it makes, I'm super proud of having created a high performance building, but I'm even more proud of having created an amazing workplace for all these people. Some of the cutting and some of the other functions that are happening. And then, there's pattern making and more sort of, office, and computer-focused tasks that are also happening in here, but also just a really beautiful workplace in what was, a very basic sort of industrial shed as the starting point. On the lower levels, the designers like to keep it dark and cool, and so you can see some of their workplaces here. There's also a showroom area, a sample library. This is where the clients come and actually work on a lot of the designs of the garments themselves. And the hallway, there's a nice plaque here that sort of talks about the team and some of the achievements that were made in terms of performance. And then, of course, the end results. Dylan, do you want to talk a little bit about the energy usage? I mean, I think the take-home message here is that the building uses even less energy than we thought it was going to use.
Yeah, and it's 60% less than what the building was previously using as well. So they saw a steep reduction in energy bills basically from doing this, which is ultimately a huge part of the why and why we do this.
Yeah, but this is a great example of one of the selling points of going through the passive house process properly, because we had this predicted energy use at the beginning of construction. Like, we knew already how much energy the building was going to be using, and this was a great thing to be able to show the client and say, when this project is completed, this is literally how much energy you're going to be using for the building. And it was amazing, first of all, to see how accurate it was, and even to be slightly better performant than what we had predicted. But for a conventional building, can kind of sort of guess, but when you go through and do a proper energy model and really drill down into all the loads, you get a model that's so accurate that you can really understand what you're going to be looking at, and they're going to be enjoying the benefits of these energy savings for decades, because it's very high quality construction. Everything is meant to last. And this is going to be, in terms of return on investment, something that's paying back year after year after year in terms of energy savings. As we mentioned up front, PHI awarded the building the pilot certificate in honor of its groundbreaking achievements, and Jessica referred to this as well in her introduction. So this was great to receive. We were very proud of the accomplishments, and of course, again, even on the certificate, you can see it's a team effort. No one of us was primarily responsible for this. It was everybody working together passionately to bring this to the finish line. Subsequently, the building was also rated as LEED Platinum, which is also nice. And just to show that Passive House can play nicely with other rating systems as well, particularly when you plug it into the performance categories. So that's kind of it. Thank you, everybody, for joining the session. Dylan and I, unfortunately, because this is recorded, won't be able to respond in real time to any questions, but we're happy to continue the discussion offline. And I would assume that some questions will be collected and passed on to us, and we'd love to hear from any of you who are either thinking about or beginning some high performance building projects in the Philippines. And I think both of our firms would love to be a resource for any of these projects in terms of helping to bring this technology and this methodology to your region. Any final words, Dylan?
No, I mean, I think he summed it up nicely. It just, I think what I'll say, it was a very rewarding project. It was my first Passive House project, and it just, I think, goes to show that you really can do anything if you put your mind to it, no matter how difficult the challenge is. And it took the whole team to do it, but we all had that mentality and came out in the end with a great building and, happy customers, happy people in the building. So
yeah, and I'll just add, you can do it too. This is the message. Like, the big message from this presentation is, if we could do it, you can do it. And particularly if you're on the ground where it's happening. I mean, we were doing this from thousands of miles away, which was challenging logistically. This is before the days that everybody was using Zoom and Teams, on a regular basis. It's so much easier if you're there in person to be able to sort of coordinate and oversee things. But for everybody that has joined this presentation, hopefully you're excited and motivated, and we'd love to start seeing some great examples of these projects in the Philippines. So thanks again, and thanks to PHI Passive House Philippines for inviting us, and feel free to reach out with any further questions. And thank you, Dylan, for joining as well.
Thank you very much.
Okay, bye-bye.
Bye.